Good morning everyone, I'm Mr. Ish. Thank you for joining me for this question where we are looking here at partial derivative, a application of that partial derivatives. In general, if you know the area for triangle is equal to half base height, there's also the other formula, half AB sine C. How does that come about? If you're looking here at a triangle which is something like this, you have a dimension A, you have a dimension B, you have a certain height, here's your right triangle, here's a certain angle. You can easily determine height. You know sine of this angle C is equal to H over A, and then H is equal to A sine C. When you plug it into the formula for area of a triangle is equal to half base and height, you have over half base, which is B, all of this, and then the height you plug in your items A sine C. Hence you get half AB sine C, which you see right over here. That's how the triangle area, this secondary area, comes about for a representation such as this. The dimensions of that triangle are given over here. You have A is equal to 30, B is equal to 40, your hypotenuse was 30, your base was 40, certain angle C is 30 degrees. We have to find these items. The change in the area of that triangle with respect to B, the change in the area of the triangle T for the total area of the triangle with respect to your C variable, and then the change in the A with respect to B. One dimension change with respect to the other dimension changing. How does the computation work? We will show you all of that. When you're looking here at these type of representations, you always focus here on your numerator value. You have a T, you have a T, you have an A, and that tells you how your equation should be. For these two questions here, your equation is just right because you're looking at something T is equal to, and you already have it, half AB sine C. When you look at this question right here, you have to convert your equation into A equals and push everything onto the other side. Before we do anything, let's just look right over here and compute the area of this triangle, half AB sine C, given these dimensions. I'm just plugging in those numbers. This starting triangle of ours has a certain area with these dimensions, and what are they? It's 30 times 40 times 30 sine, which is your sine C, divided by 2. It has an area of 300 units squared. We'll plug it in over here, we may need it. Now let's look here at the first question. I'm looking here at this change in the area, the rate of change of the area with respect to the B. And how do I do it? Well, you treat everything else as a constant. You treat these items here as your variables. What is my constant? A, half, and C. So I'll have here A sine C over 2, and the derivative of B will be just a 1. I plug in my items which I have, and it'll give me my rate of change of the area with respect to B. What's A sine C? I have a 30. And then sine C, which is a 1 over 2 over 2. I have a 30 divided by 2, 15 over 2, and that right here is my answer, and it should be right. The rate of change of the area with respect to B is equal to 15 over 2. We're not focusing too much on units, but keep in mind it's a positive value. We are looking here at a representation which is positive. As the rate of change of the B dimension increases, so must that for the area. It will be correct. Look here at this next one, the partial derivative with respect to T and the C. Now I have to look at this. What are my constants? A, B, and 2. I have here A, B over 2. What's my derivative of sine C? It'll become a cosine C, and this right here will be my template, my equation, into which I will now use those items to determine the rate of change of the area with respect to the angle C. I bring in my values. I have a 30, I have a 40, divided by 2, cosine of 30, you know that to be root 3 over 2. You compute this. You have these 2's which are 4, they come in here 10 times. I have a 300 root 3, and it should be correct, and it would be a positive value. As the angle increases in terms of its dimension, as the rate of the angle is going to increase, so must the rate at which the area increases, and it makes sense. You can picture it almost in your head. You have a certain representation which is like this. As this angle is becoming larger, your other dimensions will correspondingly increase. So will your height, so will your hypotenuse, and then the total area must increase. It makes sense. This answer here, 300 root 3, should be correct. We end with this last one, rate of change of A with respect to B. Partial derivatives coming through. This is what I have, rate of change of A with respect to B. Now how do I present my equation? You know you're looking here at something which is A equals. So take this equation and solve for A. I have total area times 2 divided by B sine C should be equal to A. What are your variables? Well, your variables are going to be only what you see over here, A and B. Your constants are C, the 2, and the T. So you solve it out. You're looking here at A is equal to, let's write it in a better way, 2T times B to the minus 1 over sine C. When you bring in derivative, which is only this, because this right here is the only variable. This here is a variable. When you do it, you're easily going to bring the partial derivative of that, but we don't have to worry about that in terms of representation. This is a variable which is affecting this side over here. Going to have a minus 2t over b squared sine c, and this right here will be the item which will come right over here. The derivative of b to the minus 1 using the power rule is minus b to the power of minus 2, but you can bring it down here and get rid of the negative exponent. The minus remains. So that's what we have. Let's publish it for you right over here. I have a minus 2t over b squared sine c. And now you see why we determined the area at the very beginning, the 300, because it can come right over here. If you did not determine that 300 from the beginning, what you can really do over here, substitute. I have minus 2 times the formula for t, which is half ab sine c divided by b squared sine c. You'll see the sine c will cancel out. This b will cancel out with this. You'll be left here with the 1 or 2 cancelling out. You'll be left here with a minus a over b. You can do this minus a over b and just plug in your values, and you have a minus 3 over 4, minus 30 over 40, minus 3 over 4. Or you can just do my way, plug in the items. You'll have a minus 2 times 300 divided by b squared, which is a 1600. Perhaps this is a harder way. This is the easier way. We already know our answer is minus 3 over 4 sine c, which is 1 over 2. And we compute it. When you compute it, we'll just use this as a check. This should be the same as our minus 3 over 4, and it will be. These two zeros cancel out. I have here a minus 6. The 2 comes on top. I have here a minus 12 over 16. When you simplify it, you have minus 3 over 4, and it should be correct. It will be a good answer. But we're having here a negative. What does a negative imply over here? The negative here implies that if the area was to be kept constant and the angle was to be kept constant, as one dimension was increased, the other one must decrease. It makes sense. And you can picture that in your mind. On the side, you can do it on your own. But you're seeing again here, when you're doing the partial derivative with respect to a and b, the t, the total area, and the angle were kept constant. Therefore, as one must increase over time, the other one must decrease with respect to that time or the experiment or whatever it is that you're doing. Hence, you're seeing a negative over here. You're not having here correspondingly positive value outcome. As one goes up, the other one goes down to maintain the area while the angle is kept constant. So that's right there at the end of this particular video. You're seeing the partial derivatives are coming into play. As one is derived or differentiated with respect to your question, the other items are held constant. So keep that in mind. When you're doing partial derivatives, it doesn't mean you're not doing a derivative or you're doing a half a derivative. You're still doing a complete derivative, but you're doing a complete derivative of the variable which is involved. Everything else, even if it looks like a variable, is treated as a constant. Thank you for watching.